So we had a lot of different measures of center, or what was typical from section 3.1. But in section 3.2, we want to try and figure out not what the center of our data is, we want to figure out how spread out the data is. How much variability is there in your data set? So let's look at the example that's on the handout in front of you. We've got two starting heights of some basketball teams. And if you'd like, we can give some names, or we can just keep them, name Team 1 and Team 2. Yes. Now, if you total this, if you total this, each of these columns, we end up with 365 for both of them. So, all right, the same total for each of them. That's good. But what's that say about the average, or what's the mean height of the players on these teams? Yeah, it will be the same. And what is that mean height? Yeah, 73. So you just divide this by 5. Let's call this a sample. So that's x bar is 73 for Team 1, and x bar is 73 for Team 2. So is that it? Are these teams identical? Do they match up evenly with each other just because their means are the same? No. What would you say is different about these then?
Team 2 has larger outliers.
Yeah, on the high end, you get some guys that are really, really tall on this team, right? And on the low end, you've got this guy. Now, I don't know as though you remember him, probably before your time, but there was a basketball player by the name of Spud Webb. Spud Webb was 5'7", and he played professional basketball. He was good. He could dunk the ball. 5'7". Man, that's like Calvin Johnson type vertical leap. That's really, really good. So, in any case, 5'7", yeah, that can happen on a basketball team. But let's look back at our data, though. There's more going on than just the fact that these two teams have the same average height. Let's plot them across that number line and try and understand a little bit more about the data. So we'll do Team 1 in pink. So their heights are 71, 72, 73, 73 again, and then way up here at 76. So that's Team 1. Likewise, let's do Team 2. I'll do that one in purple, below the line. And kind of got to squeeze this one in a little bit. Got somebody down here at a height of 67. Then up here at 70. Then at 71. And then way out here at 78 and 79. So that's the plot of our data. Is there some feature that looks like it's not being described when we say, oh, gee, the mean is the same for both of them? What's not being described here?
The amount of deviation between each point.
Yeah, the amount of deviation from that mean. So the mean was 73. So x bar equals 73. But it seems like there's a lot more spread around that mean in this data set than in this one. Team 2 has much more variability. And we're going to try and capture that variability in different ways to measure this. So an easy way to try and capture that variability is with something called the range. So for Team 1 and Team 2, let's look at the range of our data set. So Team 1, Team 2. Now I just said top minus bottom being very informal. You'd probably see it as maximum minus minimum if you're reading in the book. But what's the range of heights for Team 1? 5. And how about Team 2? What's the range of heights there? 12. Thank you. So the range at least is hinting at what we're seeing visually. Visually, we're seeing there's a lot more variability in this data set than there is this data set. Now that's a good start on our project to try and find how much variability there is in this data set. But it doesn't go quite far enough. The problem with just using the range is that you've got a lot of data, but your range is based on two values, right? Just those two. Anything could be happening in between, and you're not really capturing that. It's just based on the two values. So you're throwing out a lot of data by using the range. So what else can we do? Well, here, let me just do this for you. You kind of sit back and relax a little bit. Let me put in the heights of our athletes here into a spreadsheet, and just kind of relax and follow along a little bit as somebody would create their own version of some kind of measure of variability. So let's see here. Well, one way to start finding the variability, in fact, you hinted at it, is compare it to the mean, right? So let's compare all these to the mean. I'll take this and take that value and subtract off the mean. The mean in this case was 73. And let's do that for my entire data set. So I'll copy that formula, Control C or Command C, depending if you're Mac or PC. And now let's total it all up. So that's the sum. Let's total it all up, and whoops, I get a big fat 0. Well, what's happening is that the mean is in the center of your data. So some of your data is above the mean, some of your data is below the mean. And if you subtract off that mean and then add up all the differences, you're always going to get 0. So as a measure of variability, always getting 0, probably not all that good. The problem is that some of this was positive and some of it was negative. So, okay, what I can do then is I can square both of these. I can square this, and that's going to get rid of the negative sign, and I don't have to worry about that negative canceling things out anymore. So equals, and then come over here, raise to the second power, and let's copy that all the way down. And at least now when I sum things up, I'm not going to get something that's negative anymore. So equals, and then the sum of all these. I said not negative. I'm not going to get anything that's going to cancel out, so I'm not going to get 0. I get 14. So what we've got so far, if you were looking at this as a calculation, would look like this. You're taking the sum of x minus x bar and squaring it. That's what we've calculated so far, and we got 14. The problem with this is that if I add more data, the sum is just going to get bigger. So what we do is we kind of take an average of this, sort of. Now when you average things, you add it up and you divide by n. But for reasons that I'll explain a little bit more later, instead of dividing by n, we're going to divide by n minus 1. And this thing here is going to be something called the variance. So I'm using an S here because that's going to be the sample variance. This is the sample variance. And there's still kind of a problem with this. Now I could take, following along here, the variance of this data set would be this. Let's see, let's go here, 14 divided by n minus 1. Well, there's 5 pieces of data here, so I'll divide by 4, and I'll get 3.5. That's the variance. There's still kind of a little problem with the variance here, using the variance, and that is the units for the variance don't match our original units. If our original height is in inches, then the units of variance are in squared inches. So if I wanted to get back to the original unit, what could I do? Take the square root. Take the square root on both sides. Well done. Hopefully you'll sign up for my algebra class if you do statistics. All right, so if I take the square root on both sides, then I get the sample variance. And that's on your sheet. Just give me a sample of the standard deviation. And that's on your sheet right here. Sample standard deviation. So standard deviation, it's going to be the square root of your variance. Well, let's see what that is for this particular calculation. So if I want the square root of that, equals SQRT of this. There you go. About 1.87. And that's good. Standard deviation is a nice measure of how much variability there is in a data set. Now, I took you through this so you can appreciate some of what's going on with the standard deviation. I can do a sound check here. Still get sound? Everyone laugh? All right, you got to work on that. So now I talked you through the creation of this statistic. And this is what somebody did a long time ago when they were working with numbers and said, you know, I need something to measure variability. But we're not going to have to calculate it like this. This is a brute force approach. There's a much better way to calculate statistic or this statistic with one push of the button. Yes, ma'am.
So is that like the, if you say like this is the percentage, like give or take like this much, that would be like the give or take part?
Yeah, so what the standard deviation here represents is, you know, it's a measure of how much variability or how much spread there is in the data. So it's comparing it to the mean, and it's saying on average, in some kind of average sense, your data is about 1.87 units away from the mean, is roughly what that's saying. Now, what I want to do is a couple things. First of all, let's calculate the standard deviation the way that you're going to do it if you had a Google spreadsheet or an Excel spreadsheet. So here, if you got the data typed in, just these 5, here's what you're doing. If you don't have it typed in, take a minute, type it in. You type in equals stdev, and then let it finish it off. If you type the enter key, it'll finish it off. Standard deviation of what? Well, of this data. So we'll click that column. Wow, a lot faster, huh? A lot faster. You are not going to have to calculate it the long way. In fact, let's send this into oblivion, delete, and shift left. There we go. All right, nice. Now, if you didn't do the first one, let's do the second one. So the second team had heights of 67, 70, 71, 78, and 79. Now I'm going to calculate the standard deviation for this team. Do you expect the standard deviation to be higher, lower, the same? What do you expect from the standard deviation here? What's that? Higher? Hope it's higher, right? I mean, visually, and at least with the range, it looked like there was more variability in our data set. And if the standard deviation is doing any good at all, it should reflect that higher degree of variability. So let's try it. stdev of this data, and bam, 5.24. So it looks like it's doing what it says. So standard deviation from team 1 is roughly 1/3 of what it is for team 2. Okay, so good. That's exactly what we would hope for in some kind of a measure of variability. Standard deviation is a good measure of the variability in a data set. So let me pause here for a second. Are you okay with this measure? Now, I've summarized here for you a few of the things that you should know about the standard deviation. First of all, based on the way we calculated this, remember, you're summing up a bunch of squares. This number has always got to be positive. Always got to be positive or 0. Can you think of a case in which the standard deviation would be 0? what would have to happen to get a 0 here?
No variability in like the data.
Yeah, no variability in the data. Basically, you had the heights of a bunch of clones, right? So you're measuring the clone army. Oh, they're all 5'9". There's 0 variability. Okay, so that would give you a standard deviation of 0. Other than that, your standard deviation is going to be some positive number. And the higher it is, the more variability in the data that you're going to see. Now, sometimes what you can do is you can compare the standard deviation to the size of the mean, just to kind of get a relative sense of what's going on. And that gives you something called the coefficient of variation. What that's good for is comparing variability across two different types of data sets. So let's take a look, for example, at problem number 24. Problem 24 talks about customers in two different banks. No, not two different banks, the same bank, but different lines. How long did you have to wait in line at the different banks? Well, in one of these, you're going to wait in a line that takes this many seconds, and the other one you take, this many seconds. So let's take a look at the coefficient of variation here for these two different banks. I'm going to kind of help out the calculation a little bit with some numbers. We will get back to and discuss some more about variability, and I'll give you a chance to calculate the mean and standard deviation yet again. All right, so for a single line, customers had to wait an average of 429 seconds. Excuse me, 429, with a standard deviation of 28.6 seconds. You could also look at the range if you wanted to, subtract the top minus bottom. The range of times was 72 seconds. If you're waiting in individual lines, you have the same average, 429 seconds. Here the standard deviation is 109.29. And the range was 348 seconds. So we're going to calculate the coefficient of variation. Find out, compared to the mean, how much variability was there. So coefficient of variation is going to be the standard deviation divided by the sample mean times 100%. In this particular case, we've got 28.6 divided by 429 times 100%. That should give you about, 6.7%? 28.6 times 100 divided by 429. Yeah, about 6.7%. Do you expect a higher or lower coefficient of variation from the other line? Should be higher. The range was higher, the standard deviation is higher, so we expect something higher. And that higher coefficient of variation just says that, all right, relatively speaking, these people are waiting longer. So 109.29, 429 times 100. This time you get a coefficient of variation of, let's see, 109.29, of about 25.4, 25.5%. Okay, so it's just reflecting that there's much more variability in the data. Let's go back to our team here. In fact, team 1. And play around with them a little bit. Suppose that this is the height of team 1 in high school, and you follow them into college. And by the time they get to college, they all grow 3 inches. So I'm going to take this column and add 3 inches to the height of everybody. So equals column 1 plus 3, and I'll just copy that for the rest of this. Now the average height here, and remember average and mean are the same thing. You can type it, average height here was 73. What do you think the average height here is going to be? How has the average been affected? Should go up by 3, right? So let me see if I can just copy this formula here and paste it here. I can. How do you think the standard deviation is going to change or not? What's going to be the standard deviation of their heights over here? Should be the same thing, right? Because all you did was you shifted them. The variability is still the same. There's still a difference of just 5 inches between the height of the tallest and the height of the shortest. But the spread of the data hasn't changed. You just picked it up and moved it. So again, standard deviation is telling us what we would expect. It's talking about the spread of the data, not where the data is. Where the data is the average or the mean. There's a couple other things about standard deviation that I want to go through. One of them is on your sheet here. But are we okay so far with this notion of standard deviation? I mean, understanding what the standard deviation is the important thing. I'm not going to be asking you to calculate it by hand. What I want you to do is being able to interpret it. So that's where we're going to spend our time. I've got 2 different calculations for standard deviation. One's based on a sample, one's based on a population. One is a statistic and one's a parameter. Which one of these do you think is the statistic? Yeah, sample goes with statistic and the population goes with parameter. So this is your statistic, S. And this is your parameter, sigma. For the most part, they're calculated the same. You're going to take your data, subtract off the mean, sum that up, divide by, in this case, n minus 1, and then take the square root. Here, subtract off your mean. The mean is now the parameter mu, but it's still the mean. Square it, etc. But this time you're dividing by n as opposed to n minus 1. So that's a little bit of a difference in your data, or excuse me, in your calculation. By dividing by a bigger number, that's going to make this quotient smaller. And the sample standard deviation is always, always, always going to be bigger than the population standard deviation. The only time that they're actually going to be equal is if the standard deviation was 0 for both of them. That's the only time they're going to be equal. I've got a data set in here that we're going to work with in a minute. And it talks about, now you know what, it might be the data set we just used for coefficient of variation. But this is in the graphing calculator. You can enter and do all these statistics on a graphing calculator. You would go to the stat button, press enter to edit, enter in all your values, then quit. Then you get a nice set of summary statistics by going back to stat and this time to calculate. Now, I'm not going to ask you to do these off of this, But I want to point out one little thing about the statistics here that you get. You get a lot of them. And pretty soon when we start using StatDisk, you're also going to get a lot of them. You get the mean, you get the sum of all your data. You get the sum of the data squared. Then you've got the standard deviation, the sample standard deviation, and the population standard deviation. You're getting those two. And notice that the population standard deviation is a little bit lower than the sample standard deviation. Okay. There's other statistics that you're going to get here, and in kind of a highlighted way, let's take a look at one of them. Down here, what do you think MED is short for? Median. So this separates the top half of the data from the bottom half of the data. There's a ton of statistics you can generate just at the push of the right button. One of the things that understanding the standard deviation does is it allows us to discuss something called the empirical rule. Now, the empirical rule applies to bell-shaped data, or data which is normally distributive. So that'd be stuff like we have down below, bell-shaped curve. But that's an important assumption. Without this assumption, you can't apply the empirical rule. So the empirical rule says that most of your data, a little bit more than 2/3 of your data, lies within one standard deviation of the mean. If you go out 2 standard deviations from the mean, now you get 95% of your data. 3 standard deviations of the mean, virtually all of your data should lie within 3 standard deviations of the mean. 99.7% of the data should lie within those 3 standard deviations. So let's apply the empirical rule to problem number 42. Just a quick question here for how well you know your trivia. What's the average body temperature of a human? 98.6. That's what I'm familiar with. That's what I grew up knowing, etc. That 98.6 is really, really out of date. It came from a study done back near the turn of the 20th century, or in the early 1900s. There was a German physician who measured body temperatures of like 20,000 people. I mean, hats off to you. You're nothing but tenacious, right? 20,000 people. And these aren't the nice ones that you can stick on somebody's forehead and get an instant reading. You had to put it underneath an armpit or something like that. 20,000. Wow. That's a lot. Now, the thing is, the body temperature that we're familiar with, 98.6, that sounds pretty precise, right? 98.6, that's in degrees Fahrenheit. Well, this German physician did his work in degrees Celsius. He came up with 37 degrees Celsius. And if you take and convert this, 9/5 times 37 plus 32, that's where you get this seemingly artificial precision of the 0.6. It's just the fact of converting the data. In point of fact, the human body temperature has an average temperature that's different than 98.6, and at least for the data set in our book, we got a data set that says the average human body temperature is 98.2. Now, that's actually going to differ for males and females, so there's even more variability. Basically, 98.6 is not all that good. But whatever. Let's look at problem number 42 and see if we can apply the empirical rule. The average human body temperature in that data set is 98.2, with a standard deviation of 0.62 degrees. Now here's kind of a question for you. Which one of these measures should I use? Should I call this x bar, or should I call it mu? Should I call this S, or should I call it sigma? Which label do you think is more appropriate? Well, the difference is this is a statistic and this is a parameter. Which one do you think is more appropriate to use, a statistic or a parameter? Statistic, right? Because a parameter would represent data from everybody. This is just data from, a data set. It's not necessarily data from everybody. In fact, it's not. So we'll use this statistic, and let's find out, what range of body temperatures represents one standard deviation away from the mean. So one standard deviation away from the mean would be 98.2 minus 0.62 to 98.2 plus 0.62. You can do that on your calculator, you can do it on Google Sheets, whatever you find convenient. If you happen to have a graphing calculator, there is a little bit of a convenience there for you. We'll type in the 98.2 minus 0.62, and I get 97.58. And the convenience is right here. If you hit the second key, then the enter key, it'll pull up your previous calculation, and we'll just go back and make that a plus. So 98.82. So that's one standard deviation away from the mean. Julian, what percentage of data should lie within one standard deviation of the mean, according to the empirical rule? You can look at your handout. No, not 100%. Some help here? Yes, 68% of your data should lie within one standard deviation of the mean. So that one standard deviation of the mean is right here. So your mean, that's your center point, your midpoint. So plus and minus that, in this particular case, gave us a range of 97.58 to 98.92. Let's try a couple more on that one. What if we went 2 standard deviations away from the mean? So 98.2 minus 2 times 0.62 to 98.2 plus 2 times 0.62. In fact, I want you to do 2 and 3. And then hopefully people can give me some numbers. So I'll pause it for you guys. So this is my manual pause. When you find the ranges, also label the percentage of data that you should expect to be there. Okay, so what numbers were you getting on this stuff? How about here? 2 standard deviations below the mean. What place are you at there? Thank you. 96.96 to what? Yep, 99.44. Good. David, what percentage of data should be in this range here? Yeah, 95%. 95% of your data should be within 2 standard deviations of the mean, assuming that you have a bell-shaped distribution. Cool. Thank you. How about 3 standard deviations away from the mean? Where are we there? From what to what? Perfect. 96.34 to 100.06. And what percentage of the data should be in this range? 99.7. So virtually all of your data should be within 3 standard deviations of the mean. Let's get you there. Okay, so depending on how far you go, you're going to get 1, 2, or 3 standard deviations away from the mean. You're going to find certain percentages of data. Obviously, that's going to depend on your data set and what the mean and standard deviation is, but I do want you to have a good acquaintance with the empirical rule. What this will tell us, eventually, and we'll make this a little bit more concrete in the next section, is, okay, if these are your typical values within 2 standard deviations of the mean, then what are the atypical values? Well, it's going to be stuff that's outside of 2 standard deviations away from the mean. That's going to start to represent outlying values. And we can quantify that a little bit more in the next section. Let's go back to our handout a little bit and look some more at this calculation. So, oops. Here's the mean of your distribution. If you move up 1 standard deviation, that'll put you here. You can move 1 standard deviation down, or you can move up 2 standard deviations, or down 2 standard deviations. And by the time you move up 2 and down 2 standard deviations away from the mean, you've got 95% of your data should be here. Overall, how could I quantify that distance? How far did I move in terms of standard deviations from here to here? Plus or minus 2, but if you moved from left to right and you counted them, how many standard deviations did I move? About 4. So 4 times the standard deviation is about the range of your data. So if you wanted an approximation for the range of your data, for the standard deviation, you could divide the range by 4. That's a rough approximation for the range, assuming that your distribution is normal. Now, if you actually had the data, you wouldn't bother with this. This is only in absence of everything else. If you were given the top score and the bottom score and knew that the distribution of your data was normal, then you could approximate the standard deviation. So let's do that for some data. And now the one piece of data that they refer to in the data set, or excuse me, in the book, range rule of thumb, they're going to apply it to brain volumes, and that refers to data set 8. So we'll calculate the range rule of thumb for data set 8. Data set 8 is in Appendix B. And really what we're going to need to know for this is, are these brain volumes normally distributed? And if so, what's the maximum and the minimum? Well, if I remember this data set correctly, they don't really give you that much data to decide if it's normally distributed. We can still apply the range rule of thumb. Here's our data set, and here we go with regarding brain volumes. So there's only two numbers that I need out of this data set. Those two numbers are the maximum and the minimum. So if I want to calculate the range, I need the 1281 and the 963. So let's grab those. This is problem 2. So the range is 1281 minus, what did I say, 963. Then I can approximate S this way. 1281 minus 963 divided by 4. And that should be an approximation to the standard deviation.
79.5.
Thank you. So 79.5. The author offers up a number that was presumably calculated from the data in that data set. And the author's value, and I'm assuming that he calculated it accurately, was 124.9 cubic centimeters. Did our range rule of thumb do a good job estimating things? Not really. No, it's pretty awful in this case. Usually it's a lot better, but it would rely on the fact that your data is normally distributed. And in this case, you only had like a handful of observations. It's hard to really argue that it's normally distributed or not. Like I said, the range rule of thumb is just kind of a rough and ready thing in absence of the actual data. Most times you would actually just go through and calculate the standard deviation based directly on the data. So let's go back and do maybe a couple more of those types of calculations. So problem number 6. Football player weights. So we've seen this data set before. These are the weights of 11 randomly selected players from the roster of the Seattle Seahawks when they won the Super Bowl 48. So let's see if we can't calculate the standard deviation and then maybe answer a question based on that. So let's go back to our Google Sheets. So here's all the data. Maybe take a moment and enter that. So I'll read that off to you. It starts out with 189, 254, 235, 225, 190, 305, 195, 202, 190, 252, and 305. So let's find the standard deviation there. Remember, when you're trying to get Google or Excel to do something, you type in the equals. Type in equals stdev. Just hit enter and let it finish the rest. Should get a standard deviation of 43.86, roughly speaking. How does that compare to the mean? Well, the mean was what here? Average weight of football players in this data set is 231 pounds. So, okay. we can calculate the coefficient of variation. And let me just, I'll just put it here. Equals this times 100 divided by this. So about 19%. So there's a lot of variability in this data set. If you compare that to the variability in the data set of heights of these basketball players, it's going to be a lot less here. But that's probably because we've got different positions, and these numbers are just bigger. So you would expect perhaps more variation. Actually, maybe no. The size of the numbers doesn't have as much to do with it as the fact that there's more spread in the data. I guess the size is going to have to do with it in the extent that it allows more variability. If you had smaller numbers, you just can't have as much variability. We'll stick with that. Let's do a few more problems that ask you to do some thinking beyond just what the standard deviation represents. We'll start with problem number 10, going back to a familiar data set. Oh, Charbel? Yes. Which one? Oh, the 18? Oh, okay. That was the coefficient of variation. So what I did to get that is I took the standard deviation divided by this, the mean, and times by 100. So you're just comparing the standard deviation to its mean and then turning it into a percentage by multiplying by 100. So it means that compared to the mean, there's a lot of variability in this data set. Whereas the heights of our basketball team, coefficient of variation there is going to be pretty small. So if I take, let's do it here. If I take this, your standard deviation, times 100 divided by the mean, get a coefficient of variation there of 2.5. Here's something interesting. Remember, we followed these guys into college, right? If I calculated this, the coefficient of variation over here, is it going to be the same or is it going to be less? Well, the mean has increased. So relative to the mean, there's going to be less variability. So coefficient of variation actually decreased a little bit that way. All right, Charbel, did we answer your question though? Okay, good. Let's go back to problem number 10. Peas in a pea pod. Biologists conducted experiments to determine whether a deficiency of carbon dioxide in soil affects the phenotype of peas. So they numbered them 1, 2, 3, and 4, smooth yellow, smooth green, wrinkled yellow, and wrinkled green. 2 questions. Can we calculate measures of variation like the range or the standard deviation here for this data set? Connor, what do you think? Can we calculate measures of variation here? Let me also give you the next question. The next question is going to be, do those measures make sense? So maybe that helps you out with the first answer. Maybe some help here. Can we calculate measures of variation here? Yeah, we can. Does it mean anything though? No, because the data, you can't really average smooth yellow, smooth green, wrinkled yellow, wrinkled green, etc. I mean, averaging those colors doesn't make sense. Finding the variation of that data doesn't make sense because it's really just representative of names, nominal data. So the answer, first answer is yes, second answer is no. Let's move down to cell phone radiation. This is a good one in case you're looking at one of the problems from the homework the other day about the Coca-Cola or the different types of pop. Whistleblower measured radiation absorption rates corresponding to all these different cell phones. If one of each model cell phone is measured for the radiation, the results are used to find the measures of variation. Are the results typical of the population of cell phones that are in use? So I guess someone's shaking their head no. Do we agree? Is it typical? Is this, if I found, say, the standard deviation of this number for all these cell phones, is that going to be representative of standard deviation of cell phones that are in use? A couple votes that say no. Go ahead.
They're all kind of like outdated nowadays, right?
Yeah, all right. Those so one problem is that they might be outdated. Jonathan, you got a?
I think it's just the number of people that are using each phone service. If you have, twice as many iPhone users as
Exactly.
then you're going to have a difference.
So the other problem is that some of these are going to be more popular than others. So I don't think anyone's using a Galaxy 7 anymore, are they? At least I hope not. But your iPhone users are going to be more popular. So in order to make this representative, you'd have to weight this by how popular some of these phones are, and that's not being done. It's just you're giving each of these equal weight by just calculating the standard deviation from this data. So no, you can calculate the standard deviation, these numbers, but it doesn't really apply to the population overall. Let's take a look at problem number 20. In a study of speed dating conducted at Columbia University, female subjects were asked to rate the attractiveness of their male dates, and a sample of the results is listed below. Can the results be used to describe variation amongst attractive ratings for the population of adult males? No? Okay, it's opinionated. All right. There's one other problem here, and the author's response here kind of left me a little unhappy, because the author says, well, no, this is not generalizable because it's a voluntary response here. Voluntary response, I think we've gotten down on this idea enough in this class. I don't need to belabor it here, but if you have voluntary response data, you can't really generalize it. It's not very clear that this is voluntary response data, at least not to me. I don't know. Are you getting the impression that this is a voluntary response? Not really. I promise you that if I give you a question on a test like this, I'd make it a little bit more clear that it's voluntary response data. But I just wanted to use this one as an example or a reminder of that heading forward towards our exams. A question for you here real quick. The other day we calculated, in fact even this morning, we calculated the average of some data that was frequency data. You can also use frequency data to calculate standard deviation. Are you interested in seeing this calculation done, or is it good enough to know that it can be done? Good enough that it knows that it can be done. Good answer. All right. I'm not going to make you do this. There's certainly nice software and commands and packages that can do this pretty quickly. Maybe what I'll do moving forward is I'll have this calculation kind of already set up and show you it, but it's not something I'm going to hold you responsible for. You are responsible for knowing and understanding what S means, the standard deviation. So for instance, if I calculated standard deviation of these two different data sets and said, all right, well, which one has more variability, you should be able to compare the numerical values and say, all right, well, the data set for age of best actors has more variability than this one. In fact, it does look that way because this looks a little bit more spread out. Women seem to win it at an earlier age than some of the men. Well, they do have some outliers. So tough to say. Then the empirical rule. Now, one thing that was true about the empirical rule is that it applied to data sets that had a normal distribution. Not everything you're going to run into has a normal distribution. So what do you do if it doesn't have a normal distribution? Well, then you flip over your paper and we look at Chebychev's rule. So there's a rumor that Chebychev doesn't know how to spell his own name. Throughout my teaching career, I've seen at least 3 different spellings of Chebychev. One with a CH, one with an SH, and one with a T. So, not sure if he actually knew how to spell his own name or not, but it does sound fun. The nice thing about Chebychev's rule is that it applies to any data set. In any data set, you have at least this much data within k standard deviations of the mean. So the empirical rule, you need to have a normal distribution. For Chebychev's rule, well, it doesn't have to be a normal distribution. It can be any distribution. So for problem, I think it's number 44, asks us to find, well, how much data should be within 2 standard deviations of just any data set? So let's plug in a k equal 2 here and take out your calculators and see if you can't figure out what percentage of data should lie within 2 standard deviations of the mean. So basically, you're going to plug in a 2 there for k. 2 squared. So 1 minus 1 over 2 squared. And if you conquer that hill, then try the next one. 3 standard deviations away from the mean. You can round your answers off to the nearest percentage. Lorraine, what'd you get for the first part here? Within 2 standard deviations of the mean, how much should we expect? What percent of the data? One more time. Actually, 75. 75% of the data. All right, so 75%. Maybe you missed a decimal place somewhere. So 75% of the data should lie within 2 standard deviations of the mean. Verena, how about within 3 standard deviations of the mean? What percentage of the data should we have? Didn't get that one yet? Did somebody? Ryan? Yeah, 89% of the data. You don't have to stick to just integer values. You can do any values. How does this compare to the empirical rule? What percentage of the data has to lie within 2 standard deviations if your data is normally distributed? 95. And within 3 standard deviations? Yeah, 99.7. That's a lot. The one thing that's nice about this is you can do this for any value of k. It doesn't have to just be an integer value. So I could do parentheses 1 minus 1 divided by, I don't know, throw out a number, 2.5. We'll do 2.5 squared times 100. So we'd expect about 84% of the data to lie within 2.5 standard deviations of the mean. So, okay, still a majority, a large majority. What's the one big difference between the empirical rule and Chebychev's rule? Yeah, perfect. Well said. The empirical rule has to be normally distributed. has to use normally distributed data, and Chebychev's rule doesn't. Now this is a minimum. This is, at least this percentage has to lie within K standard deviation of the mean. It could be a lot more. Could be all of it. It's just a minimum. It's just a minimum guarantee here. All right. Guaranteed that I'm done with my discussion on section 3.2. So let me give you some homework here, and then we'll move on to section 3.3 after a couple minutes. So for homework, let's see. If you have the 12th edition, 12th edition, try 1 through 21 and 37. If you have the 13th edition, then try 1 through 21, 25, 41, and 43.